Have you ever wondered what truly happens when we die? For centuries, humanity has grappled with questions about the nature of existence, the possibility of an afterlife, and the limits of consciousness. Science, philosophy, and spirituality have all offered competing explanations, but one idea, rooted in modern physics, stands out for its profound implications: quantum immortality. Quantum immortality is a theoretical concept born from the many worlds interpretation of quantum mechanics. This idea suggests that death, as we traditionally understand it, might not be the absolute end. Instead, consciousness could persist in alternate realities, branching off at pivotal moments when survival is at stake. This isn't science fiction. It's an intriguing hypothesis that challenges our deepest assumptions about reality, mortality, and the self. In this video, we will embark on a journey to unravel the mysteries of quantum immortality. We will explore the scientific principles behind it, its philosophical implications, and the profound questions it raises about life and death. Along the way, we will delve into fascinating experiments, theoretical frameworks, and imaginative scenarios to bring this complex idea closer to everyday understanding. By the end, you might find yourself questioning not just what happens when we die, but what it truly means to live. Let us begin by laying the groundwork, the strange and counterintuitive world of quantum mechanics. To grasp the concept of quantum immortality, we must first explore the world of quantum mechanics, a branch of physics that describes the behavior of particles at the smallest scales. At this level, the rules governing reality differ drastically from what we experience in our everyday lives. One of the foundational discoveries in quantum mechanics is that particles, such as electrons and photons, can exhibit both wave-like and particle-like behavior, depending on how they are observed. This phenomenon, known as wave-particle duality, was famously demonstrated in the double-slit experiment. When particles are not observed, they behave like waves, creating an interference pattern. However, when observed, they act as individual particles, passing through one slit or the other. This discovery led to a key insight. The act of observation can influence the state of a quantum system. In other words, the mere presence of an observer appears to collapse a particle's wave function, forcing it into a specific state. Another fundamental principle is superposition, which allows particles to exist in multiple states simultaneously until they are measured. For example, an electron can be in a state of spinning both clockwise and counterclockwise at the same time. However, once observed, it adopts a single, definite state. Superposition introduces the idea of probability into the very fabric of reality. Instead of determinism, where outcomes are fixed, quantum mechanics operates on probabilities, with each potential outcome having a certain likelihood of occurring. Perhaps the most intriguing aspect of quantum mechanics is its interpretation. One of the most widely discussed is the many worlds interpretation, proposed by physicist Hugh Everett in 1957. According to this interpretation, every time a quantum event occurs with multiple possible outcomes, the universe splits into separate branches, each representing one of those outcomes. For example, imagine flipping a quantum coin. In one branch of the universe, the coin lands heads. In another, it lands tails. Both outcomes exist simultaneously, but in separate parallel universes. This framework forms the foundation for the concept of quantum immortality, suggesting that our consciousness might continue in branches where we survive life-threatening events. The idea of quantum immortality is deeply rooted in the evolution of quantum mechanics and the revolutionary theories that emerged in the 20th century. To understand its context, we must examine the key milestones and thinkers who laid the groundwork for this speculative concept. Quantum mechanics was born out of necessity as classical physics failed to explain certain phenomena. Pioneers like Max Planck introduced the idea of quantized energy levels, while Albert Einstein's work on the photoelectric effect provided evidence for the particle-like nature of light. These discoveries challenged the deterministic worldview of classical mechanics, paving the way for a probabilistic understanding of the universe. The many worlds interpretation, proposed by Hugh Everett in 1957, was a radical departure from the dominant Copenhagen interpretation of quantum mechanics. While the Copenhagen view relied on wave function collapse to explain observed outcomes, Everett suggested that all possible outcomes exist simultaneously in parallel universes. This interpretation eliminated the need for collapse, offering a more deterministic view of quantum events. Everett's theory was initially met with skepticism and resistance. However, over time it gained traction among physicists and philosophers seeking a more comprehensive understanding of quantum phenomena. The many worlds interpretation provided the theoretical foundation for the idea of quantum immortality. The leap from many worlds to quantum immortality was driven by speculative thought experiments. If every possible outcome exists in a branching multiverse, could consciousness persist in the branches where survival occurs? This question bridged physics and philosophy, prompting discussions about the nature of consciousness and its relationship to the physical world. Today, quantum mortality remains a speculative idea, but it continues to inspire debate and exploration. Advances in quantum computing, neuroscience, and artificial intelligence may eventually shed light on the questions it raises. While the concept is unproven, it serves as a thought-provoking lens through which to examine the mysteries of existence and the potential of the multiverse. Quantum immortality takes the many worlds interpretation a step further by connecting it to human consciousness and survival. It suggests that in situations where death is a possible outcome, your consciousness could continue in the branch of the universe where you survive, even if countless other branches exist where you did not. To understand this, imagine a hypothetical scenario. You are part of an experiment involving a quantum device that can result in either life or death depending on the spin of a particle. Each time the device activates, there are two possible outcomes. In one universe, you survive, in another, you don't. According to quantum immortality, your conscious experience would continue in the universe where you are alive, even if another version of you has perished in a different branch. This raises profound questions about the nature of consciousness. If quantum immortality holds true, it implies that consciousness is not tied to a single physical existence, but can persist across multiple realities. This challenges conventional views of life and death, suggesting that, subjectively, you might never experience the cessation of your own consciousness. While Schrödinger's cat is often used to illustrate superposition, let's consider a fresh analogy. Imagine standing at a crossroads in a dense forest with two paths ahead. One path leads to safety, the other to danger. As you step forward, the universe branches, and in one reality you find safety, in another you face peril. Quantum immortality suggests that your conscious experience would always align with the path leading to survival, even if countless other versions of you meet different fates. This idea shifts the focus from abstract particles to a deeply personal context, making the concept more relatable while retaining its scientific essence. Quantum immortality is more than just a theoretical concept. It touches on profound philosophical questions about life, death, and the nature of existence. Traditionally, death is viewed as the end of consciousness and personal identity. Quantum immortality challenges this notion by suggesting that, subjectively, one might never experience death. This raises the question, is death merely a transition between branches of the multiverse? For the individual, the experience of continuity could blur the boundary between life and death. This theory forces us to reconsider the essence of consciousness. If our awareness persists across branches, does it imply that consciousness is not strictly tied to a physical brain? Could consciousness be a fundamental aspect of reality, akin to space and time? These questions open new avenues for both philosophical inquiry and scientific exploration. Quantum immortality also has ethical implications. If our actions create new branches of reality, are we morally responsible for the outcomes in those branches? Moreover, the idea of eternal survival in some form could alter our perspective on risk, meaning, and purpose in life. Does the possibility of quantum immortality diminish the value we place on our current existence? or does it enhance our appreciation of life's complexity? By exploring these philosophical dimensions, we can better understand the broader implications of quantum immortality and its potential to reshape our worldview. The concept of quantum immortality intersects with philosophical traditions and beliefs across cultures, offering a unique lens through which to explore humanity's timeless questions about life, death, and existence. In Eastern traditions such as Hinduism and Buddhism, the idea of reincarnation resonates with the core premise of quantum immortality. Both suggest a continuity of consciousness beyond physical death, albeit with different mechanisms. In Hindu philosophy, the Atman, soul, transcends the physical body, while in Buddhism, the cycle of samsara reflects the rebirth of consciousness influenced by karma. These beliefs parallel the notion of consciousness persisting across alternate realities in the multiverse. Friedrich Nietzsche's concept of eternal recurrence, where all events repeat infinitely in a cyclical timeline, bears similarities to quantum immortality. Although not tied to quantum mechanics, it invites reflection on the infinite possibilities of existence. Additionally, Cartesian dualism, which separates the mind and body, aligns with the idea that consciousness could transcend physical boundaries and persist independently. Abrahamic religions such as Christianity and Islam often emphasize the continuity of the soul in an afterlife. While the metaphysical underpinnings differ from quantum mechanics, the shared focus on eternal existence echoes the implications of quantum immortality. These perspectives raise ethical and existential questions about accountability, morality, and the nature of identity in an infinite multiverse. Contemporary philosophers engage with quantum immortality by addressing its implications for personal identity and ethics. If consciousness diverges into multiple branches, how do we define self? Does the existence of countless versions of you diminish individual significance, or does it underscore the uniqueness of each moment? These debates highlight the profound impact of quantum immortality on our understanding of existence. Belief in quantum immortality, whether as a scientific possibility or a philosophical curiosity, can have profound psychological effects on individuals. For many, the idea of quantum immortality can alleviate the fear of death. If consciousness is perceived as persisting across alternate realities, the traditional view of death as the end of existence may no longer hold. This perspective can provide comfort and reduce existential anxiety. Belief in quantum immortality might influence how individuals approach risk and decision-making. If one believes in survival in some form, they may become more willing to take bold actions, knowing that their consciousness might continue in another reality. This belief can inspire deep existential reflections on the meaning of life and the consequences of one's actions. The idea of infinite survival challenges individuals to consider what truly matters in their lives and how their decisions resonate across potential realities. Conversely, the notion of infinite survival might provoke anxiety in some individuals. The idea of endlessly navigating branching realities could feel overwhelming and raise questions about the nature and desirability of immortality. The concept of existing in multiple realities can lead to a re-evaluation of personal identity. If countless versions of you exist, how do you define who you are? This question can encourage introspection and growth, but may also create feelings of fragmentation or uncertainty. By examining these psychological dimensions, we can better understand how quantum mortality resonates with individuals and influences their worldview. While quantum immortality is an intriguing concept, it is not without its criticisms and challenges. These issues highlight the limitations of our current understanding and the speculative nature of the theory. One of the most significant challenges to quantum immortality is the absence of direct experimental evidence. While the many worlds interpretation provides a theoretical framework, there is no practical way to test or observe the survival of consciousness across different branches of the universe. The speculative nature of this idea makes it difficult to validate scientifically. Quantum mechanics is primarily concerned with the behavior of particles at microscopic scales. Critics argue that applying these principles to macroscopic systems, such as human consciousness, may be an overreach. The leap from quantum particles to the subjective experience of survival introduces complexities that remain unresolved. Some philosophers question the underlying assumptions of quantum immortality. For instance, if consciousness continues in one branch after death, what happens to the versions of you that perish in other branches? This raises questions about identity and the continuity of the self. If quantum immortality implies that an individual will always experience survival, does it encourage recklessness? Could this idea undermine the perceived consequences of risky behavior, leading to ethical concerns about responsibility and accountability? These challenges emphasize the need for further exploration and refinement of the theory. While quantum mortality opens new avenues of thought, it also underscores the limitations of our current knowledge about consciousness and the nature of reality. Quantum immortality's implications extend beyond individual survival to broader existential risks, reshaping how humanity might approach challenges that threaten our collective existence. If survival is perceived as inevitable in some branch of reality, does it alter how we address risks such as climate change, pandemics, or nuclear conflict? While quantum immortality might suggest that humanity persists in certain branches, this perspective could lead to complacency or diminished urgency in addressing critical global challenges. Belief in quantum immortality could embolden humanity to take greater risks in exploration and innovation. For instance, the drive to colonize other planets or develop groundbreaking technologies might be pursued more aggressively, with the understanding that failure in one branch does not preclude success in another. The notion of infinite survival raises ethical questions about accountability and responsibility. If actions that lead to catastrophic outcomes are mitigated by survival in other branches, how should we evaluate the morality of risk-taking? This perspective challenges traditional ethical frameworks, requiring new ways of assessing the impact of our decisions across multiple realities. Quantum immortality also invites consideration of collective consciousness. If humanity's survival branches into infinite outcomes, how do we define progress or success? Multiverse ethics, a theoretical framework, could emerge to address moral dilemmas across parallel realities, fostering a more holistic approach to existential risks. By integrating these perspectives, quantum mortality not only reframes individual existence, but also compels humanity to rethink its collective trajectory in an interconnected multiverse. Despite its speculative nature, quantum immortality sparks curiosity and prompts us to think about its potential applications and implications for the future. Research into quantum immortality could shed light on the mysteries of consciousness. By exploring the interplay between quantum mechanics and human cognition, scientists may uncover new insights into how awareness arises and whether it has a quantum basis. The concept of consciousness persisting across branches of reality raises questions about artificial intelligence. Could advanced AI systems one day develop a form of awareness akin to human consciousness? If so, might they also be subject to principles of quantum immortality? Quantum immortality might also influence how we approach space exploration. If survival is perceived as inevitable in some branch of reality, could this alter the risks we are willing to take when venturing into the unknown? This perspective might encourage bolder exploration while raising ethical questions about accountability and responsibility. In the grand tapestry of existence, the concept of quantum immortality invites us to confront our most deeply held beliefs about life, death, and the universe itself. It bridges the gap between cutting-edge physics and timeless philosophical questions, challenging us to expand our understanding of reality. While the theory remains speculative, it serves as a powerful tool for reimagining the boundaries of human experience. Whether or not quantum immortality reflects the true nature of existence, it underscores the importance of curiosity, exploration, and the relentless pursuit of knowledge. In contemplating this concept, we are reminded of our profound connection to the cosmos and to each other. Quantum mortality challenges us to see life not as a singular journey, but as an infinite unfolding of possibilities. It inspires us to live fully, embrace uncertainty, and continue asking the questions that drive discovery and growth. As we continue to uncover the mysteries of the cosmos, Quantum mortality reminds us that the greatest discoveries often lie at the intersection of science, philosophy, and imagination. Let us embrace these questions, not as endpoints, but as beginnings, inviting us to explore the boundless potential of existence.
Does reality truly exist if no one is observing it? How can two particles on opposite sides of the universe instantly influence each other? Is it possible that every decision we make creates a parallel universe? If time can reverse at the quantum level, what does that mean for our future? Could the human brain operate like a quantum computer? Are we living in a reality where everything is invisibly interconnected? Welcome to the perplexing world of quantum mechanics, where the rules we think govern reality break down, and the universe reveals itself as something far stranger than our everyday experience suggests. The mysterious truths of quantum mechanics. Imagine tossing a pebble into a pond. The ripples spread out, graceful and predictable. Now, what if the pebble could behave both like a ripple and as a solid object at the same time? Quantum mechanics is a branch of physics that studies the smallest building blocks of the universe, particles like electrons, photons, and quarks. Yet the more we look, the less solid reality seems to become. This section will explore three of its most mysterious phenomena: wave-particle duality, superposition, and quantum entanglement. Wave-particle duality is the idea that light and matter can behave both as particles and waves, depending on how they're observed. Imagine asking someone whether a coin is heads or tails, and their answer changes depending on how closely you're looking. The double-slit experiment. In this iconic experiment, scientists shot particles, like electrons or photons, at a barrier with two slits. Behind the barrier was a screen to capture where the particles landed. Step 1. When the particles were observed closely, they behaved like tiny marbles, forming two distinct lines on the screen, one behind each slit. Step 2. When not observed, the particles acted like waves, spreading out and forming an interference pattern of many lines, as though the particles had passed through both slits simultaneously and interfered with themselves. Simplified explanation: think of a particle as a traveler facing a fork in the road. When no one is watching, the traveler takes both paths at once, exploring every possibility. But the moment you watch, the traveler chooses one path, as if responding to your gaze. Why it's strange? This suggests that the mere act of observing can change the fundamental behavior of matter. Is reality shaped by observation? And if so, what does that mean about the universe when no one's watching? Quantum superposition. In classical physics, an object is either here or there, in one state or another. Quantum mechanics introduces superposition, where particles exist in multiple states simultaneously until measured. Schrödinger's cat thought experiment. A physicist, Erwin Schrödinger, imagined placing a cat in a box with a vial of poison, which would break if triggered by a random quantum event. Until someone opens the box, the cat exists in a superposition of states both alive and dead. Imagine flipping a coin and sealing it inside an envelope. To you, the coin is both heads and tails at the same time, because you haven't seen it yet. It's only when you open the envelope that the coin chooses a side. Why it's strange? Superposition challenges the idea of objective reality. If particles exist in multiple states until observed, is the universe inherently uncertain? And how does reality decide which state to take when observed? Quantum entanglement. Entanglement occurs when two particles become so deeply connected that the state of one instantly determines the state of the other, no matter how far apart they are, even if they're on opposite sides of the universe. Einstein's skepticism. Albert Einstein famously called entanglement spooky action at a distance, because it seemed to defy the speed of light, the universal speed limit. Yet experiments have repeatedly confirmed this phenomenon. Simplified metaphor: imagine you have a pair of gloves. You send one glove to the moon and keep the other on Earth. Without looking, you don't know which is the left glove and which is the right. The moment you check the glove on Earth and see it's the left one, you instantly know the glove on the moon is the right, even though no information traveled between them. Entanglement suggests that particles can remain connected in a way that transcends space and time. Could this imply a deeper, hidden layer of reality where everything is interconnected? Questions to ponder. If observing particles changes their behavior, does that make us co-creators of reality? How can particles influence each other instantaneously across vast distances? Is the universe fundamentally random, or is there an underlying order beneath the quantum chaos? Quantum mechanics challenges our deepest assumptions about reality. Wave-particle duality blurs the lines between objects and actions. Superposition raises questions about the nature of existence, and entanglement hints at a universe where everything is interconnected in ways we're only beginning to grasp. This is just the beginning of our journey into quantum science. As we dive deeper, these mysteries will intertwine with questions of philosophy, consciousness, and the very fabric of time. But for now, quantum mechanics reminds us of a humbling truth. The universe is far stranger and far more wonderful than we ever imagined. Philosophy and quantum mechanics. Quantum mechanics doesn't just alter our understanding of physics, it challenges our fundamental beliefs about reality, existence, and the nature of the universe. It brings us face to face with questions that philosophers have grappled with for centuries. Could quantum mechanics provide the missing link between science and philosophy? In this section, we explore the fascinating relationship between quantum theory and philosophical inquiry. The observer effect. Does reality exist without observation? The observer effect in quantum mechanics suggests that the mere act of observing a quantum system can change its behavior. In the famous double-slit experiment mentioned earlier, particles like electrons or photons behave as waves when unobserved, and as particles when observed. But here's the philosophical twist. If observation affects reality, then can we really say that the world exists independently of us? Does the universe only decide its state when we look at it? This is a powerful philosophical question that echoes the debate about whether existence requires a mind to perceive it. Simplified explanation. Imagine you're trying to catch a butterfly in the wild. Every time you approach it, the butterfly flutters away, changing its position and behavior. If you stand still and don't try to catch it, the butterfly behaves in its natural way. The act of trying to catch it or observe it changes what it does. This is like what happens at the quantum level. Our attempt to measure something changes its state. Philosophical connection. This idea mirrors solipsism, a philosophical theory that suggests only the mind of the observer can be known to exist. In quantum mechanics, it's almost as if reality isn't truly there until we observe it. Could our minds actually be shaping the world around us? If so, what does that say about free will and our place in the universe? Questions to ponder. If the act of observing creates reality, what does that say about the world when we're not looking? Can we ever truly know the universe if our perception of it always shapes it? The multiverse hypothesis, a universe for every possibility. Quantum mechanics also suggests that, when faced with multiple possible outcomes, particles don't just pick one, they exist in all possibilities simultaneously until measured. This leads to the many worlds interpretation, which proposes that every time a quantum event occurs with multiple possibilities, the universe splits into separate branches, each representing one of the possible outcomes. Essentially, every decision, every quantum event creates a new universe. Simplified explanation. Imagine you have a coin and you're about to flip it. In the quantum world, the coin doesn't just land on heads or tails, it lands on both, in separate worlds. In one universe, it's heads, in another, it's tails. Every possible outcome of every quantum event exists in its own parallel universe. This theory raises the idea of determinism versus free will. If every possible outcome exists in a parallel universe, does that mean we're simply along for the ride, with no true choice? Or does the fact that we experience one outcome imply that we are actively shaping our reality? Questions to ponder. If there are infinite universes, does it mean all possibilities are actualized, or is there still a guiding hand behind it all? What does this say about the role of free will in our lives? Are we simply living out one branch of the many possibilities? Determinism versus free will. Does the quantum world allow for both? In classical physics, the universe was thought to be deterministic. Everything happens because of prior causes, like the turning of a clock. But quantum mechanics doesn't fit this model. Quantum mechanics tells us that at the microscopic level, events are not entirely predictable and chance plays a significant role. This creates an interesting paradox when thinking about human behavior. Is everything determined by the laws of physics, or do we have the power to make choices that aren't preordained? Think of a rolling dice. Classical physics would say the dice's outcome is determined by its starting position, how fast it rolls, and all the forces acting on it. But in quantum mechanics, the dice could land on several faces at once, and it's only when we look at it that we see which face it lands on. Could our decisions be more like this quantum roll of the dice? This aligns with a long-standing philosophical debate. Is our universe deterministic, where everything happens for a reason, or is there room for randomness and free will? Quantum mechanics, with its inherent unpredictability, seems to suggest that randomness plays a role in shaping our world. But what does that mean for the human experience of choice? Questions to ponder. If quantum mechanics allows for randomness, does that free us from being controlled by the laws of physics, or does it create a different kind of order? How does this randomness relate to the concept of free will? If we're free to choose, is it random, or is there a deeper purpose behind our decisions? In this section, we've explored how quantum mechanics doesn't just change our view of the universe, it compels us to revisit age-old philosophical questions. From the observer effect's challenge to objective reality, to the multiverse's implications for free will, quantum theory forces us to reconsider what we think we know about existence. Quantum mechanics isn't just a tool for physicists, it's a bridge between science and philosophy, urging us to ask deeper questions about the nature of reality, consciousness, and choice. As we continue to explore these ideas, we'll see how quantum mechanics intertwines not only with the smallest particles, but also with the deepest questions about our place in the cosmos. Quantum mechanics and consciousness. The intersection between quantum mechanics and consciousness is one of the most intriguing and speculative areas in modern science. Does quantum theory hold the key to understanding consciousness? Could our minds be operating on quantum principles, giving rise to thoughts, emotions, and self-awareness? This section explores how quantum mechanics might be connected to the very nature of consciousness, blurring the lines between physics, philosophy, and psychology. Quantum brain hypothesis. Could the brain work like a quantum computer? One fascinating theory is that the brain could operate like a quantum computer, using the principles of superposition and entanglement to process information in ways classical computers can. The idea is that quantum effects might be occurring within our neurons, influencing how we think, perceive, and experience the world. Imagine trying to solve a puzzle by checking all the possible answers one at a time. A classical computer would do this in a linear fashion, one possibility after another. But a quantum computer, using superposition, could check all possibilities at once much faster. If our brains worked this way, it could explain the speed and complexity of human cognition. Supporting evidence. Some scientists point to microtubules, tiny structures within our neurons, as potential quantum processors. These microtubules might be able to support quantum states, which could allow the brain to process vast amounts of information at incredible speed. The hypothesis was notably proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff in their theory of orchestrated objective reduction, which suggests that consciousness arises from quantum processes within the brain. Why it's fascinating? If the brain operates on quantum principles, it would mean that our minds could be far more complex than we currently understand. It might also explain the subjective quality of consciousness, why we experience thoughts and emotions rather than simply processing information like a computer. Questions to ponder. If quantum mechanics is involved in consciousness, could we ever fully understand how thoughts arise? Could quantum processes help explain the hard problem of consciousness? Why subjective experience arises from objective brain activity? Panpsychism and quantum physics, consciousness in every particle. Panpsychism is the philosophical theory that consciousness is a fundamental property of all matter. In other words, everything down to the tiniest particle has some degree of consciousness. Some proponents of this view argue that quantum mechanics could provide the framework for understanding how consciousness pervades the universe. Simplified explanation. Imagine you have a drop of water. In classical physics, you could describe it purely by its physical properties, its weight, its temperature, etc. But what if, on a deeper level, the molecules inside the water also had an awareness of their environment? Panpsychism suggests that consciousness isn't limited to humans or animals. Instead, it's a fundamental feature of the universe. Quantum connection. Quantum mechanics hints at the idea that consciousness could be an intrinsic feature of matter. For example, quantum coherence, the ability of particles to remain in a superposition of states, could be the physical manifestation of a deeper, universal consciousness. This idea aligns with David Bohm's theory of the implicate order, which suggests that everything in the universe is interconnected through a deeper layer of reality that could also involve consciousness. Why it's fascinating? If consciousness is embedded in the very fabric of matter, it suggests that the universe itself could be conscious. In this view, every atom, every photon, and every quark might have a tiny, rudimentary form of awareness. This could radically change how we think about the mind-body problem and our relationship with the universe. Questions to ponder. If every particle has consciousness, does that mean we are connected to everything around us in a profound way? Could quantum processes in particles explain the nature of subjective experience? Integrated Information Theory, IIT. Could the universe itself be conscious? One of the most ambitious theories of consciousness is integrated information theory, developed by neuroscientist Giulio Tononi. IIT proposes that consciousness arises from the degree to which a system can integrate information. The more interconnected and integrated the system, the more conscious it is. This theory suggests that consciousness might not be limited to humans or animals, but could be a property of any system that integrates information in a sufficiently complex way. Think of a light bulb. When it's on, it illuminates the room, but when you turn off the switch, the light goes out. In a way, the light bulb integrates the flow of electricity, but it's not conscious. Now, imagine a more complex system, like the brain, which integrates vast amounts of information across billions of neurons. According to IIT, the more information that's integrated, the higher the level of consciousness. Quantum connection. If IIT is correct, and consciousness is about integrating information, then quantum mechanics could play a key role. Quantum coherence, the ability of quantum systems to remain in a state of superposition and interact with one another, might allow for a higher level of information integration. In this way, the quantum world might help explain the emergence of consciousness in complex systems. IIT could provide a framework for understanding not only human consciousness, but also the consciousness of the universe itself. If the universe is a vast network of interconnected systems, each integrating information in complex ways, could it be that the universe itself has some form of awareness? Questions to ponder. If IIT is correct, could the universe be conscious in the same way that our brains are conscious? What would it mean if the universe as a whole had an awareness of its own existence? In this section, we've explored how quantum mechanics could be linked to consciousness, offering new possibilities for understanding the mind. From the idea of the brain operating as a quantum computer, to the radical suggestion that consciousness may be a fundamental property of matter, quantum theory opens up new avenues for thinking about awareness and existence. Quantum mechanics, with its strange and counterintuitive properties, challenges our understanding of reality, and in doing so, it may be pointing us toward a deeper, more interconnected view of consciousness. If consciousness arises from quantum processes, the universe might be far more conscious than we ever imagined, perhaps even in ways we are yet to comprehend. Quantum mechanics and time. Time is something we all experience, seconds ticking by, days passing, and memories fading as the years go on. But quantum mechanics suggests that time might not be as straightforward as we think. In fact, quantum theory challenges our most basic understanding of time, raising deep philosophical questions about its true nature. Could time be more fluid than we've ever imagined? Is it a fundamental part of the universe, or could it be an illusion? In this section, we'll explore how quantum mechanics reshapes our concept of time and what it means for our understanding of the universe. Non-linearity of time. Does time flow in one direction? In classical physics, time flows in one direction from the past to the future. This idea is deeply rooted in the second law of thermodynamics, which states that entropy, or disorder, tends to increase over time, creating a natural arrow of time that moves forward. However, quantum mechanics presents a different picture. At the quantum level, time may not flow in a strict, linear fashion. Imagine you're watching a movie. As the story progresses, things happen in sequence, first this, then that. But at the quantum level, the sequence of events might not always be fixed. It's as though you're watching a movie where the scenes could play in any order, and the story might change depending on your perspective or how you're observing it. Time itself could be much more flexible than we experience it in our daily lives. Why it's strange, in quantum mechanics, particles don't always behave as though they follow a strict timeline. For instance, certain quantum processes can seem to reverse time, where particles appear to go backward in time, which challenges the idea of a universally directed flow of time. Quantum mechanics example. Quantum particles can travel backward in time according to the Feynman diagrams in quantum field theory. These diagrams depict particles as traveling through both forward and backward directions in time, essentially reversing the arrow of time under certain conditions. Questions to ponder. If time can flow backward at the quantum level, what does that say about our perception of the past, present, and future? Could the experience of time we have in our everyday lives be an illusion, a consequence of our limited perspective? Time reversal symmetry. Could time run backward? One of the most mind-bending implications of quantum mechanics is the idea of time reversal symmetry. This principle suggests that the laws of physics are the same whether time flows forward or backward. If you could rewind a quantum process, the physics would work just as they did going forward. In other words, if you could reverse the motion of a quantum system, it wouldn't violate any physical laws. Think of a video of a ball bouncing. If you play it backward, the ball seems to jump up from the floor, defying gravity. But in the quantum world, the ball's behavior would not change if played backward. The particles and forces involved would still obey the same fundamental rules, whether time is moving forward or backward. Why it's strange, time reversal symmetry in quantum mechanics challenges our everyday experience. We never see time rewinding in the macroscopic world. We observe things breaking, aging, and decaying in one direction only, forward. Yet, at the quantum level, particles behave as though they could reverse direction, suggesting time itself may be a construct based on our perception. At the subatomic level, certain particles, like photons and electrons, behave symmetrically under time reversal. If you were to reverse the direction of time for a quantum event, the system would evolve in precisely the same way, leading scientists to wonder if time's flow is an artifact of our observations. Questions to ponder. If time is reversible at the quantum level, does that mean our concept of time itself is just a mental construct? Could this symmetry have real-world consequences, such as in the development of time travel technologies? Quantum time travel. Is time travel possible? Could quantum mechanics make time travel possible? While time travel has long been a staple of science fiction, quantum mechanics opens the door to a theoretical possibility. The strange behaviors of particles at the quantum level, like superposition and entanglement, suggest that time may be more flexible than we realize. Could we, in theory, travel backward or forward in time? Simplified explanation. Imagine you're standing at a fork in the road, and both paths lead to the same destination. In classical physics, you can only take one path, but in the quantum world, there's a chance both paths are traveled simultaneously, with each one existing in a different timeline. It's as if you're living in two parallel realities, one where you choose one path, and another where you take the other. While actual time travel is still the stuff of fiction, some theoretical physicists suggest that quantum mechanics could allow us to move through time in ways we can't fully comprehend yet. One of the key ideas here is wormholes, theoretical shortcuts in space-time that could allow travel between different points in time and space. Quantum mechanics example. A specific type of quantum phenomenon called closed time-like curve suggests that time loops where the future influences the past could exist within the framework of general relativity. These theoretical time loops have been studied in the context of quantum particles, and they might be the key to understanding time travel. Questions to ponder. If quantum mechanics allows for time loops, could we travel back to the past and change history? What would happen to the laws of causality if time travel were possible? Quantum mechanics fundamentally challenges our understanding of time. From non-linearity to time reversal symmetry and the possibility of time travel, quantum theory presents a view of time that's far from the fixed, unidirectional flow we experience in our daily lives. At the quantum level, time is not an absolute, steady force, it's a malleable, fluid aspect of the universe. As we continue to explore the relationship between quantum mechanics and time, we may find that our perception of reality itself is shaped by deeper, quantum-level processes. Perhaps, in time, the mysteries of time travel, time reversal, and the true nature of temporal flow will be unraveled, giving us an entirely new perspective on our place in the universe. Imagine yourself drifting silently in the vastness of space. Before you, a galaxy spins a luminous whirlpool of billions of stars, gas, and dust. The core glows brilliantly, surrounded by spiraling arms stretching out like cosmic ribbons. It's a mesmerizing dance of light and motion, held together by a gravitational force so immense it defies comprehension. Yet, hidden within this stunning spectacle is an enigma. The visible elements of the galaxy stars, planets, and nebulae account for only a fraction of the mass needed to sustain this intricate ballet. What is holding these celestial bodies together? What invisible force anchors the galaxy's swirling arms, ensuring it doesn't fly apart? This is the mystery of dark matter, the unseen framework of the universe. It doesn't emit light or energy, making it undetectable by traditional telescopes. Yet its gravitational pull shapes galaxies, clusters, and the universe itself. It is the scaffolding upon which the cosmos is built. The idea of dark matter arose when astronomers noticed discrepancies between what they could see and the behavior of galaxies. In the 1930s, Fritz Zwicky, a Swiss astrophysicist, observed that galaxies in the Coma cluster were moving faster than expected. By applying Newtonian physics, he calculated that visible matter alone couldn't generate enough gravity to hold the cluster together. There had to be some missing mass providing the necessary gravitational glue. Decades later, Vera Rubin and Kent Ford confirmed this phenomenon within individual galaxies. Studying the rotation curves of spiral galaxies, they discovered something astonishing. Stars on the outer edges of galaxies were moving just as fast as those near the center. According to the laws of gravity, this was impossible unless there was an unseen mass extending far beyond the visible boundaries. This realization that most of the universe's mass is invisible reshaped our understanding of the cosmos. Today, scientists estimate that dark matter constitutes roughly 27% of the universe, dwarfing the mere 5% made up of ordinary matter. The rest, even more mysterious, is dark energy. The invisibility of dark matter sets the stage for one of science's greatest pursuits. It's a riddle that challenges the boundaries of our knowledge, compelling us to peer deeper into the fabric of reality. What is this unseen force? How does it interact with the visible universe? And what does its existence mean for our understanding of life, existence, and everything in between? The hunt for dark matter isn't just about solving an abstract puzzle. It's about uncovering the fundamental truths of the universe. If we can understand this invisible force, we might unlock secrets about how galaxies form, why the universe expands as it does, and perhaps even glimpse the forces that shape the cosmos in its infancy. This is the unseen force shaping our universe. It surrounds us, permeates us, and holds the cosmos together. To understand dark matter is to understand the universe itself. And so, the quest begins with questions as vast and profound as the galaxies swirling in the night sky. To uncover the presence of something unseen, scientists rely on the subtle traces it leaves behind. One of the most compelling pieces of indirect evidence for dark matter comes from the phenomenon of gravitational lensing, a striking consequence of Einstein's theory of general relativity. Gravitational lensing occurs when the gravity of a massive object could produce. This discrepancy points to the presence of an unseen mass surrounding and permeating these galaxies. Dark matter, though invisible, exerts a gravitational influence that reveals itself through these cosmic distortions, allowing astronomers to see its effects, even if they can't directly observe the matter itself. Another key piece of evidence for dark matter comes from the rotation curves of galaxies, graphs showing the velocity of stars and gas as a function of their distance from the galactic center. In a galaxy governed solely by the visible matter, you'd expect the stars further from the center to orbit more slowly, similar to how planets in our solar system move. This is because gravity weakens with distance, and the mass producing the gravitational pull would primarily reside in the dense, star-filled core. However, observations tell a very different story. When Vera Rubin and her colleagues measured the rotation speeds of stars in spiral galaxies, they found that these velocities remain nearly constant, even at great distances from the galactic center. This flat rotation curve implies the existence of a vast, unseen halo of mass extending far beyond the visible stars. Without this invisible matter, the stars at the outskirts of the galaxy should be flung off into space, unable to maintain their high velocities. The logical conclusion: a massive halo of dark matter envelops the galaxy, providing the necessary gravitational pull to stabilize the outer stars. Gravitational lensing and galaxy rotation curves are two sides of the same coin, each offering a glimpse of dark matter's pervasive role in the universe. Together, they form a consistent narrative. There is far more to the cosmos than meets the eye. Dark matter doesn't just shape individual galaxies, it influences entire clusters. In fact, gravitational lensing studies of massive galaxy clusters reveal intricate maps of dark matter's distribution, showing how it congregates in enormous structures that act as the scaffolding of the universe. These clusters themselves are stabilized by dark matter's immense gravitational influence, just as individual galaxies are. These indirect observations highlight the ingenuity of science. Without the ability to see or directly interact with dark matter, researchers rely on its gravitational footprints to trace its existence. Each distorted image and unexpected star velocity is a clue, bringing us closer to understanding the unseen. While the nature of dark matter remains elusive, these pieces of evidence confirm its presence beyond reasonable doubt. Dark matter is not a theoretical abstraction, it is a tangible force shaping the universe. Its detection may be indirect, but its impact on the cosmos is undeniable. Dark matter is enigmatic not just because it's invisible to the naked eye, but because it interacts so weakly, if at all, with ordinary matter. This makes its direct detection an extraordinary challenge, requiring experiments of unparalleled sensitivity and precision. Despite these hurdles, scientists have devised ingenious methods and cutting-edge facilities to attempt what might seem impossible: capturing evidence of dark matter directly. The Large Hadron Collider, LHC, located at CERN in Geneva, is the world's most powerful particle accelerator. With its 27-kilometer ring buried underground, the LHC smashes protons together at nearly the speed of light, creating conditions similar to those that existed moments after the Big Bang. These high-energy collisions produce a cascade of particles, which are meticulously analyzed by detectors to search for anomalies, potential fingerprints of dark matter. Scientists at the LHC are particularly interested in detecting WIMPs, or weakly interacting massive particles, a leading candidate for dark matter. The theory suggests that WIMPs might be created during these collisions. If WIMPs exist, they could appear as missing energy in the data, escaping the detectors without interacting, much like neutrinos. While no conclusive evidence for dark matter has yet emerged from the LHC, the experiments have provided valuable constraints, narrowing the range of possible properties that dark matter could possess. The search continues with upgraded detectors and refined collision parameters, as researchers hope to one day spot dark matter particles among the debris of their high-energy collisions. Deep underground, shielded from cosmic rays and other background noise, lies the Large Underground Xenon or Lux detector, one of the most sensitive instruments ever built to hunt for dark matter. Located in the Sanford Underground Research Facility in South Dakota, Lux relies on a tank filled with ultra-pure liquid xenon to detect the faintest interactions between dark matter particles and normal matter. The principle is straightforward but ambitious. If a dark matter particle passes through the detector and collides with the xenon nucleus, it will produce a minuscule flash of light and a small ionization signal. These signals are then captured by ultra-sensitive photomultiplier tubes, capable of detecting even the faintest whispers of activity. Although Lux has not yet observed definitive evidence of dark matter, its results have set new benchmarks for sensitivity, helping to rule out certain theoretical models. Its successor, Lux Zeppelin, is even more advanced, with a larger detector and enhanced capabilities to sift through the cosmic silence in search of dark matter's elusive presence. Beyond the LHC and Lux, numerous other experiments contribute to the hunt for dark matter. Projects like Xenon 1T in Italy, PICO in Canada, and Super CDMS in the United States employ different approaches, from cryogenic detectors to bubble chambers, to maximize the chances of detection. Each of these experiments tackles a specific aspect of the dark matter puzzle, reflecting the global collaboration and interdisciplinary innovation required to confront this profound challenge. The diversity of techniques ensures that even if one method fails, others may succeed in uncovering dark matter's secrets. The direct detection of dark matter would mark a watershed moment in physics, confirming the existence of a previously invisible component of the universe. It would provide not only answers to long-standing questions, but also open doors to entirely new realms of understanding. For now, the search continues, a testament to humanity's unyielding curiosity and determination to reveal the unseen forces shaping the cosmos. Detecting dark matter is one of the greatest challenges in modern physics. By its very nature, dark matter defies direct observation. It does not emit, absorb, or reflect light, nor does it interact with electromagnetic forces. Its presence can only be inferred through its gravitational effects, making the search akin to hunting shadows in a darkened room. Yet, these obstacles have not deterred scientists. Instead, they have fueled ingenuity, pushing the boundaries of technology and theoretical physics. The prevailing hypothesis suggests that dark matter interacts only through gravity and possibly the weak nuclear force. If true, this means that dark matter particles pass through ordinary matter almost entirely unnoticed. For context, billions of dark matter particles could be streaming through your body at this very moment, leaving no trace of their passage. This weak interaction necessitates detectors of extraordinary sensitivity. These instruments must distinguish potential dark matter signals from a cacophony of background noise, including cosmic rays, neutrinos, and even natural radioactivity in the Earth itself. To overcome this, experiments are often placed deep underground or in remote locations to minimize interference. The pursuit of dark matter demands cutting-edge technology which comes with significant costs. Facilities like the Large Hadron Collider and underground detectors like LUX or Xenon require immense financial and logistical support. Furthermore, the sheer complexity of these instruments means that even minor malfunctions can delay research for months or years. For instance, liquid xenon detectors must maintain extreme purity to avoid contamination that could mimic dark matter interactions. Achieving this level of precision requires meticulous engineering and constant monitoring, making every experiment a balancing act between innovation and practicality. One of the greatest challenges in the hunt for dark matter is the uncertainty surrounding its nature. While theories like WIMPs dominate the conversation, other candidates such as actions, sterile neutrinos, and primordial black holes offer competing possibilities. Each theory demands a different experimental approach, dividing resources and efforts. Moreover, if dark matter does not conform to these existing models, scientists may be searching in the wrong direction entirely. The possibility that dark matter interacts via unknown forces or consists of particles beyond the standard model of physics remains an ever-present challenge, forcing researchers to constantly re-evaluate their assumptions. Dark matter is not evenly distributed throughout the universe. It clusters in halos around galaxies and galaxy clusters, but its density varies significantly depending on location. Detecting dark matter on Earth might therefore be akin to searching for a single grain of sand in an entire desert, a problem of scale and probability. This uneven distribution also complicates experimental timing. Certain experiments rely on the Earth's motion through the galaxy to detect variations in dark matter particle flux. Such seasonal or directional signals are faint and require years of data collection to confirm. Despite these formidable challenges, the search for dark matter continues with unwavering determination. Each failed experiment provides critical data, narrowing the field of possibilities and refining our understanding. These incremental advances are essential steps in the scientific process, building toward an eventual breakthrough. The global effort to detect dark matter involves thousands of researchers, engineers, and theorists working collaboratively across disciplines. New experiments, like the upcoming LUX Zeppelin detector and advancements in neutrino observatories, are poised to push the limits of sensitivity even further. Theoretical physicists, meanwhile, continue to develop models that integrate dark matter into the broader framework of cosmic evolution, offering fresh perspectives and potential avenues for detection. The stakes are high. Detecting dark matter would not only confirm its existence, but also revolutionize our understanding of the universe. It could illuminate the processes that shaped galaxies, provide insights into the early moments of the cosmos, and reveal connections between the macroscopic structure of the universe and the microscopic world of particles. Above all, the pursuit of dark matter represents the essence of human curiosity. It is a testament to our drive to understand the unseen, to uncover the forces that bind the cosmos together, and to push beyond the boundaries of what is known. The Standard Model of particle physics is one of the most successful theories in science. It describes the fundamental particles, quarks, leptons and bosons, and the forces that govern their interactions, the electromagnetic weak and strong nuclear forces. With the discovery of the Higgs boson in 2012, the Standard Model seemed complete, offering a coherent explanation for much of the observable universe. However, there's one glaring problem. The Standard Model doesn't account for dark matter. While it elegantly explains the behavior of ordinary matter, it fails to include the mysterious substance that constitutes roughly 27% of the universe's mass energy content. This discrepancy has placed the Standard Model under immense strain, compelling scientists to search for extensions or entirely new frameworks. One of the clearest ways dark matter challenges particle physics is through its gravitational effects. The Standard Model has no particle capable of producing the massive gravitational influence attributed to dark matter. Neutrinos, the only Standard Model particles that interact weakly and are electrically neutral, were once considered candidates. However, their tiny masses and high velocities render them incapable of explaining the observed behavior of galaxies and galaxy clusters. Dark matter's gravitational effects indicate it must consist of a new type of particle, one that interacts weakly with ordinary matter, but has sufficient mass to shape the cosmos. This requirement forces researchers to look beyond the Standard Model for answers. Dark matter's invisibility stems from its apparent lack of interaction with electromagnetic forces. It does not emit, absorb, or reflect light, making it undetectable through traditional methods. This property places it outside the realm of particles like electrons or photons, which are central to the Standard Model. The absence of electromagnetic interaction raises profound questions about the nature of dark matter. Does it belong to an entirely new class of particles? Does it interact via unknown forces? These possibilities hint at physics beyond the established paradigm, requiring theoretical innovation. Dark matter's existence suggests that the Standard Model is incomplete. Several theories aim to bridge this gap, including supersymmetry. This theoretical framework extends the Standard Model by proposing a partner particle for each known particle. In this context, the lightest supersymmetric particle, such as a neutralino, is a promising dark matter candidate. However, the failure of experiments like the Large Hadron Collider to detect supersymmetric particles has cast doubt on this theory. Hidden sectors. Some models propose that dark matter resides in a hidden sector, a parallel universe of particles and forces that interacts with ordinary matter only through gravity or other weak interactions. This idea introduces exotic particles like actions and sterile neutrinos as potential dark matter candidates. Modified gravity. While not a particle-based solution, some physicists explore the idea that our understanding of gravity itself may be incomplete. Theories like modified Newtonian dynamics challenge the need for dark matter by suggesting that gravity behaves differently on cosmic scales. However, these theories struggle to match the evidence provided by phenomena like gravitational lensing. Dark matter doesn't just challenge the Standard Model, it opens a window into uncharted territory. If dark matter particles are discovered, they could revolutionize our understanding of the universe's evolution, the forces that govern it, and the underlying structure of reality itself. Such a breakthrough might unify disparate areas of physics, from the quantum scale to cosmological structures, offering insights into long-standing mysteries like the nature of gravity and the origins of the universe. Among the myriad theories proposed to explain dark matter, WIMPs, or weakly interacting massive particles, stand as the frontrunners. WIMPs are hypothetical particles predicted to have masses much greater than that of protons, yet they interact only weakly with ordinary matter. This means they can pass through stars, planets, and even our bodies without leaving a trace. The appeal of WIMPs lies in their compatibility with the thermal relic hypothesis. In the early universe, particles were created and annihilated in high-energy interactions. As the universe expanded and cooled, most of these particles decayed or annihilated, but some remained. The predicted abundance of WIMPs aligns closely with the observed density of dark matter, making them a compelling candidate. Another promising dark matter candidate is the action, a hypothetical particle much lighter than WIMPs. Actions arise from solutions to theoretical problems in the Standard Model, specifically the strong CP problem, which involves the behavior of quarks and gluons in quantum chromodynamics. Unlike WIMPs, actions are extraordinarily light and interact extremely weakly with both matter and radiation. What makes actions fascinating is their potential to form a vast, invisible field permeating the universe. These particles could also account for the observed rotation curves of galaxies and other gravitational phenomena attributed to dark matter. Ongoing experiments such as the Action Dark Matter experiment aim to detect actions by searching for their predicted interaction with electromagnetic fields. Sterile neutrinos are an extension of the Standard Model's neutrinos, but differ in a crucial way. They do not interact via any of the known forces except gravity. These heavier, sterile counterparts of regular neutrinos could constitute dark matter if they were produced in sufficient abundance in the early universe. Sterile neutrinos are intriguing because their decay could emit detectable X-rays. Observations of unexplained X-ray emissions from galaxies and galaxy clusters have fueled interest in this candidate, though no definitive evidence has yet emerged. A more unconventional candidate for dark matter is primordial black holes. Unlike particle-based explanations, primordial black holes are compact objects that might have formed shortly after the Big Bang. These black holes could range in size from microscopic to many times the mass of the Sun and might account for at least part of the universe's dark matter. Although primordial black holes do not require exotic new particles, their presence would profoundly impact our understanding of cosmology and the early universe. Studies of gravitational lensing and cosmic background radiation are ongoing to determine whether primordial black holes could explain the observed effects of dark matter. The diversity of dark matter candidates reflects the breadth of the challenge. Beyond WIMPs, actions, sterile neutrinos, and primordial black holes, researchers explore other possibilities including superfluid dark matter, a theory suggesting that dark matter could form a quantum superfluid, influencing gravity in unique ways. Fuzzy dark matter, extremely light particles with wave-like properties that could form large-scale structures. Self-interacting dark matter particles that interact with themselves but not with ordinary matter, potentially explaining certain galactic phenomena. Each candidate represents a different facet of the dark matter puzzle. WIMPs dominate collider and underground detection efforts, while actions and sterile neutrinos push the boundaries of particle physics. Primordial black holes and exotic theories challenge the very concept of what dark matter might be. The search for these candidates is a testament to the creativity and adaptability of science. Whether dark matter turns out to be a familiar particle or something entirely unexpected, its discovery will revolutionize our understanding of the cosmos and the laws that govern it. The discovery of dark matter would revolutionize our understanding of the universe's history and structure. Currently, dark matter is considered the invisible scaffolding upon which galaxies and larger cosmic structures are built. By unraveling its nature, we could answer fundamental questions about how the universe formed, evolved, and reached its present state. In the early universe, shortly after the Big Bang, dark matter played a crucial role in shaping the cosmic web. While ordinary matter interacted with light and radiation, dark matter remained unaffected by electromagnetic forces, allowing it to clump together under gravity. These clumps served as gravitational wells, pulling ordinary matter into them and forming the seeds of galaxies. Discovering the properties of dark matter would refine our models of these early processes, offering a clearer picture of how galaxies, stars, and planets emerged. The universe is structured in a vast, interconnected web of galaxies, clusters, and voids. This cosmic web is shaped by the gravitational influence of dark matter. Without it, these structures would not exist as we observe them today. If dark matter's properties were identified, such as its mass, interaction strength, or particle behavior, scientists could better simulate the universe's large-scale evolution. These insights would bridge gaps in our understanding of how cosmic structures formed over billions of years, and how they continue to evolve under the influence of both dark matter and dark energy. Dark matter's role isn't limited to the past, it also shapes the future. The gravitational pull of dark matter counters the expansive force of dark energy, which drives the acceleration of the universe's expansion. Understanding the balance between these forces could help predict the ultimate fate of the cosmos. If dark matter interacts in ways we don't yet understand, it could influence whether the universe continues expanding forever, eventually freezing in a heat death, or contracts in a big crunch. Alternatively, if dark matter decays over cosmic timescales, its diminishing influence could allow dark energy to dominate, leading to even more rapid acceleration and a big rip. By identifying and studying dark matter, physicists could refine these scenarios, offering profound insights into the universe's destiny. Dark matter discovery would unify two seemingly disparate realms of physics, the quantum and the cosmic. At its core, dark matter likely consists of particles governed by quantum mechanics, yet its influence is felt on the largest scales, shaping galaxies and the universe itself. This connection might lead to breakthroughs in other areas of science, such as particle physics. Discovering dark matter particles could expose new forces or symmetries in nature, leading to extensions of the standard model. Astrophysics, understanding dark matter would refine models of star formation, galaxy dynamics, and black hole behavior. Cosmology, insights into dark matter could provide clues about the universe's earliest moments, potentially shedding light on inflation or other processes near the Big Bang. Beyond the scientific implications, discovering dark matter would profoundly impact how humanity views its place in the cosmos. It would reveal that much of the universe consists of something fundamentally different from the matter that makes up our bodies, our planet, and everything we've ever known. This realization could deepen our sense of connection to the cosmos, emphasizing that we are part of a much larger, more mysterious whole. Perhaps the most exciting implication of discovering dark matter lies in the doors it could open. Historically, every major scientific breakthrough has led to unexpected discoveries. Electricity paved the way for modern technology, and quantum mechanics revolutionized our understanding of the universe. Similarly, understanding dark matter might reveal entirely new realms of physics, forces, or phenomena that we cannot yet imagine. In this sense, the discovery of dark matter is not just about solving a mystery, it's about expanding the boundaries of human knowledge, venturing into the unknown, and uncovering truths that could redefine our understanding of existence itself. Dark matter plays a fundamental role in cosmology, the study of the origin, evolution, and structure of the universe. Its gravitational influence serves as the backbone of cosmic structures, dictating how galaxies form, cluster, and evolve over billions of years. Without dark matter, the cosmos as we know it would not exist. Understanding dark matter is therefore essential to refining our models of the universe's formation and its large-scale behavior. In the early universe, just after the Big Bang, dark matter began to clump together under gravity, forming dense regions that acted as seeds for galaxy formation. Ordinary matter, composed of atoms, was initially scattered by intense radiation, but eventually fell into these dark matter wells, creating the galaxies and clusters we see today. Without dark matter, this process would have been impossibly slow, leaving a universe largely devoid of structure. Exploring dark matter is key to unraveling these early cosmic events. The universe is expanding, a fact first discovered by Edwin Hubble in the 1920s. Over time, this expansion has been found to be accelerating, driven by a mysterious force called dark energy. Dark matter and dark energy together dominate the universe, comprising approximately 95% of its total mass energy content. Their interplay shapes the dynamics of the cosmos. Dark matter slows the expansion through its gravitational pull, while dark energy pushes against it, driving acceleration. Understanding dark matter is critical to deciphering this delicate balance, the tug-of-war. How dark matter and dark energy interact influences the rate of cosmic expansion. Precise knowledge of dark matter's properties, its density, distribution, and interactions would allow cosmologists to make more accurate predictions about the universe's future trajectory. The ultimate fate of the universe, whether the cosmos ends in a big freeze, big crunch, or big rip, depends largely on the role and behavior of dark matter over cosmic timescales. The lambda called dark matter is the prevailing framework in cosmology. It describes a universe composed of dark energy, dark matter, and ordinary matter. While lambda called dark matter has been extraordinarily successful in explaining observations like the cosmic microwave background radiation and large-scale galaxy distributions, it remains incomplete without a deeper understanding of dark matter. Structure formation, simulations of galaxy and cluster formation depend heavily on assumptions about dark matter's properties. Better understanding could resolve discrepancies between observed and simulated galaxy distributions. Small-scale anomalies. The lambda-called dark matter model struggles to explain certain small-scale phenomena, like the observed density profiles of dark matter in galaxies. A deeper understanding of dark matter could address these inconsistencies. Studying dark matter may also provide insights into the universe's infancy. Shortly after the Big Bang, conditions were so extreme that matter and energy were indistinguishable. Dark matter's behavior during this epoch could reveal clues about the inflationary era, the rapid expansion of the universe immediately following the Big Bang. Baryogenesis, the process by which ordinary matter came to dominate over antimatter. Reionization, the period when the first stars and galaxies began to form, reionizing the universe's neutral hydrogen. By connecting the properties of dark matter to these events, cosmologists could fill gaps in our understanding of the universe's earliest moments. Dark matter research also has profound implications for understanding dark energy, the force driving cosmic acceleration. While these two phenomena are distinct, they are deeply intertwined in shaping the universe's fate. Studying dark matter may reveal new physics that unifies them, providing a more complete picture of the universe's mass energy content and its ultimate destiny. Understanding dark matter would mark a paradigm shift in cosmology, akin to Copernicus' heliocentric model or Einstein's theory of general relativity. It would not only refine our knowledge of the universe's expansion, but also reveal the fundamental processes that govern the cosmos. By answering the question of dark matter, we edge closer to answering the larger questions. Where did we come from? Where are we going? And what is the true nature of reality? The discovery of dark matter would be a watershed moment for particle physics, opening a door to realms of knowledge far beyond the Standard Model. While the Standard Model has been remarkably successful in describing the known particles and forces, it cannot account for the mysterious substance that makes up 27% of the universe. This glaring gap suggests the existence of entirely new particles, forces, or symmetries that extend the boundaries of our current understanding. If dark matter is composed of particles, discovering its true nature could revolutionize our understanding of the subatomic world. Among the most promising avenues are WIMPs. Weakly interacting massive particles as leading candidates, WIMPs would represent a new class of particles interacting via weak nuclear forces. Their discovery could reveal new interactions and extensions to the Standard Model, such as supersymmetry, which posits the existence of partner particles for all known particles. Actions. The discovery of axines would solve not only the dark matter mystery, but also the strong CP problem in quantum chromodynamics. Actions could provide a bridge between particle physics and cosmology, unveiling connections previously thought unrelated. Sterile neutrinos. These hypothetical particles, unlike their Standard Model counterparts, would only interact through gravity. Detecting sterile neutrinos could expand our knowledge of neutrino physics and offer insights into the behavior of other elusive particles. Each of these particles represents a possible paradigm shift, revealing interactions or dimensions of nature that are currently hidden from view. Dark matter could point to the existence of previously unknown forces or interactions. For example, dark sector physics. Some theories propose that dark matter interacts with itself through dark forces mediated by particles analogous to photons in the visible universe. Detecting these forces could unveil an entirely new layer of reality, a dark sector that exists parallel to our observable universe. Fifth force of nature. If dark matter interacts with ordinary matter in unexpected ways, it might hint at a new, fundamental force beyond the four currently known: gravitational, electromagnetic, strong nuclear, and weak nuclear forces. These discoveries would fundamentally alter our understanding of how the universe operates, potentially unifying disparate phenomena under a broader theoretical framework. One of the most profound implications of dark matter research lies in its potential to connect quantum mechanics and general relativity, two pillars of modern physics that remain theoretically incompatible. Dark matter operates on both quantum and cosmic scales, offering a rare opportunity to study phenomena that could unify these frameworks. If dark matter consists of quantum particles with wave-like properties, its behavior might illuminate how quantum effects manifest on macroscopic, gravitational scales. Understanding dark matter's gravitational effects could provide insights into quantum gravity, bringing us closer to a theory of everything. The hunt for dark matter has driven advancements in technology that benefit particle physics more broadly. High-energy experiments like those at the Large Hadron Collider are continually upgraded to achieve greater sensitivity, paving the way for discoveries beyond dark matter. Innovations in detector design, such as cryogenic techniques and ultra-pure materials, are already being applied to explore other unanswered questions in physics. These advancements not only enhance our ability to detect dark matter, but also improve our capacity to explore phenomena like neutrino oscillations, proton decay, and the asymmetry between matter and antimatter. The discovery of dark matter would necessitate extending the Standard Model to include new particles, interactions, and symmetries. Such an extension could reveal connections between seemingly unrelated phenomena, such as dark matter and the Higgs field, provide a framework for understanding other cosmic mysteries like dark energy or the origins of matter-antimatter asymmetry, offer insights into the conditions of the early universe, such as the processes that occurred during and after the Big Bang. The breakthroughs in particle physics spurred by dark matter research would ripple across multiple disciplines, from astrophysics to cosmology. These discoveries could redefine fundamental concepts such as mass, force, and even the nature of reality itself. As our theoretical frameworks evolve, so too will our ability to answer deeper questions about existence. As we conclude this journey through the unseen universe, one truth remains abundantly clear: dark matter is one of the greatest mysteries of our time. Its discovery and understanding hold the potential to reshape not only physics, but our very perception of reality. Yet, for all that we've explored its gravitational fingerprints, its hypothesized particles, and its role in the evolution of the cosmos, dark matter remains tantalizingly elusive. This mystery is a reminder of the vastness of the unknown. The universe is far larger, more complex, and more wondrous than we can currently imagine. Dark matter is but one piece of a much larger puzzle, one that includes dark energy, the origins of the universe, and the fundamental nature of existence itself. The ongoing quest to understand dark matter is a testament to human curiosity and ingenuity. It represents the best of science, a relentless pursuit of knowledge, driven by the belief that the answers lie just beyond our reach. With each experiment, each observation, and each theoretical breakthrough, we inch closer to uncovering the secrets of the cosmos. But dark matter is more than a scientific challenge. It's a source of inspiration. It invites us to dream, to question, and to wonder. What lies hidden in the fabric of the universe? What new realms of physics await discovery? How will these insights transform our understanding of the cosmos and of ourselves? The future of dark matter research is bright, filled with promise and potential. Advancements in technology, from more sensitive detectors to next-generation particle accelerators, bring us closer to direct detection. New telescopes and space missions will map the cosmos with unprecedented precision, revealing the subtle influences of dark matter on galaxies and beyond. Meanwhile, theoretical physicists continue to push the boundaries of what is possible, exploring ideas that might seem unimaginable today, but could become the discoveries of tomorrow. Each step forward in the hunt for dark matter deepens our understanding of the universe, reminding us that the pursuit of knowledge is never truly finished. As we unravel this mystery, we'll inevitably uncover new questions, new frontiers to explore, new challenges to face, and new wonders to marvel at. So, as we look to the future, let us embrace the mystery of dark matter. Let it remind us of the infinite possibilities that lie within the cosmos, waiting to be discovered. The journey to understand dark matter is far from over, but every step we take brings us closer to answering the fundamental questions of existence. What is the universe made of? Where did it come from? And what is our place within it? In the end, the greatest discoveries often begin with the simplest yet most profound realization: the universe is far more mysterious than we could ever imagine. And that mystery in itself is the ultimate source of wonder.